Okay, then here we go. Lesson 3, video number 3 that I'm producing, available in both Google Meet and YouTube formats. A quick review of what we've done so far. We've got these energy level diagrams, and we know that electrons can move from one level to another, but they can't stop in the middle. It's got to be a whole energy level, like rungs on a ladder, or none at all. So I've got an incoming photon, and if I've got an electron down here, the electron can absorb the energy of the incoming photon, and the electron can move up a level. And we know that the electrons can move up levels in smaller or larger steps. Now, the same is, or the opposite really, of that process is where an electron is already at some higher energy level. For instance, it's up here. And when the electron jumps back down, then energy is emitted. And this could also be as a photon of light. The energy that's absorbed, let's have a look at this one here. The energy that is absorbed in this jump going up is exactly the same as the energy emitted when the electron goes down the same jump. So if you go from the bottom level, I'll call this E0, call this E1, call this one E2. If the electron goes from E0 to E2, then it absorbs a certain amount of energy. Let's say it absorbs 5 units of energy. When the electron goes back down the same levels from E2 to E0, it will emit the same 5 units of energy. So that's just a little review there. Now, energy absorbed and energy emitted leads to different types of spectra, which is what we're going to do now. So the first spectrum I want to look at is called the continuous spectrum. Now, we've already seen the continuous spectrum in the refraction section. And how do you get a continuous spectrum? You take a hot source, something like the sun, for instance. And the sun's beaming out light in all directions, and some of it's going to come to us. So we'll take a beam of light that's going to come to us. We're going to pass it through a prism, and we know that we're going to get this continuous Roy-Gabiv spectrum being produced, okay, from our prism. So what does a continuous spectrum look like if it's nice and colorful? Here we go. It looks just like that, and you'll be very familiar with that. That's like a rainbow type spectrum. So continuous spectrum we've already done. Okay, so not much time being spent on the continuous spectrum. I want to move on now to a second type of spectrum, and the second type of spectrum is called an emission spectrum or spectra. Okay, now what does that look like? What it looks like is this here, and it's mainly black, but with different colored lines on it. Okay, so we can write down something about that. So emission spectrum. So it has a black background with individual colored lines on it, and the different colors relate to the wavelength of the light, because every different color's got a different wavelength. So it's got a different wavelength. And where can you find information about these wavelengths if you wanted to look up the wavelength of that red line, for instance? You could go to the data sheet and it will give you some information about the specific wavelength of that red light or green light or blue or whatever. Okay, be aware that there are slightly different colors because the continuous spectrum is quite broad. So here's my continuous spectrum, and red goes from there to there. So you could have a line here, or you could have a line here, and they would both appear to be red, but they might have slightly different wavelengths. So you need to be careful which red you're choosing. And gases, I've already mentioned this, that different gases produce different colored wavelengths, and we'll come back onto that. So you could look up red and you might find that you get red. This particular color of red could come from hydrogen, and this particular color of red could come from some other different element. So you need to be aware that you can get slightly different colors produced by slightly different elements. And again, you'll have that in the data table. Okay, so that's emission spectra. Black background with individual colored lines. Each color has a different wavelength. Look up the information in the data table if you need it. The next one I want to do, you need to get all this written down, of course. We're going to have a look at the absorption spectrum. And an absorption spectrum looks like this one in the middle. So I've talked about continuous spectrum, which gives you a complete continuous range of colors. The emission spectrum, black background with different colors present. The absorption spectrum is a background of the continuous spectrum, but it's got colors missing. And you can see that where the colors are missing, there's a missing bit of red, and the missing color is a red line. And there is a missing bit of green, and the missing bit's green. And it's no coincidence, actually, that there's a very close similarity between the absorption spectrum and the emission spectrum, that this line that's missing, this color that's missing in the absorption spectrum, can appear as one of the only lines. This missing line in the absorption spectrum can appear as one of the lines in the emission spectrum. So what's the absorption spectrum? An absorption spectrum, and you need to get this written down. It's got a background of the entire visible spectrum. And to be precise, the entire visible continuous spectrum, because that's a word we've just learnt. With individual black lines. That show where energy has been absorbed. Okay, note absorption has got a P in the word, but where energy has been absorbed, that's got a B in the word. I don't know why, but there are two different words. Absorption, that's the name of the spectrum, and the process is where energy has been absorbed, has got a B in it. Okay, so we've done actually some of this stuff before at National 5. And I want to just have a quick look at these lines that appear in the emission spectrum. And each individual element in the periodic table produces its own emission spectrum. Certainly did that at National 5 in the space physics section. And here, for instance, are some emission spectra of different elements, and every element has got its own different emission spectrum. So it's got its own black background with lines superimposed on the top. I know this might be a little bit difficult to see, but if you just do some Googling for continuous absorption and emission spectra, you'll be able to get these much clearer than seeing these little pictures on your small screen. I suppose I could try and hold it up there, and you can see one of these a little bit better if I can hold it still. And every individual element has got its own emission spectrum. So if you've got an unknown piece of material that you've just found somewhere, this is used quite a lot in forensic analysis. You've got some material, you've not got a clue what it is. What do you do with it? You can take that material and you can heat it up. It will produce light, it will glow. We talked about that in the first video. It will turn into a gas, it will produce light, and you can then analyze in a thing called a spectrometer or a spectrograph. You can analyze the light, and then you can tell what elements are there. Obviously, this is just the single element of carbon, but if you had a sample of mysterious material and it contained carbon and iron, you'd get these two different spectra, one for carbon and one for iron, and you get them superimposed upon each other. And then it's just the job of picking them out and saying, well, these are the elements that are there individually, even though the lines are superimposed. And you would have seen that, if you can remember that, in the space physics section. So every element's got its own different emission spectrum. Right, let's move on again. What's the actual physical process that causes these spectra? Well, let's have a look at this, and you'll get a YouTube video. If you don't want to watch me doing this, you can go straight to a YouTube video, and I've put in how do these get produced, and there's a very good short video about this. I'm going to take a little bit longer. So how are these produced? How are spectra, not what do they look like, which you'll need to know, but how are spectra actually produced? Well, we've done just a little bit about the continuous spectrum, and what you need is something like the sun. You need something called a hot source, and it will produce a continuous spectrum. I don't think you need to know much more than that. It's got to be something like the sun, and the sun is described as a hot source. How do we get the emission spectrum? And what you want is probably just a single gas, a hot gas, which is glowing. We talked about this earlier. You take a tube of gas like hydrogen and you pass electricity through it, and it will produce this thing called a line emission spectrum. And again, go and have a look at the video. Just make sure you've got all this written down. So we've covered that. One I want to look at in a little bit more detail is what happens if you get a hot source like the sun, like sunlight, and the SQA specifically talk about the sun as a hot source, and then you view the continuous spectrum after the light from the hot source, the sun, has passed through a cold gas. So a hot source viewed through a cold gas, and that will give you your absorption spectrum. And I'm going to spend just a little bit of time explaining what goes on here with this absorption spectrum and its relationship to the SQA requirements that we need to have a look at. Okay, now the first person who did this, who looked at a hot source viewed through a cold gas, was somebody called Fraunhofer. And you need to know this name, Fraunhofer. Okay, so that's something we need to have a look at. So what we're going to, this is particularly an absorption spectrum that Fraunhofer looked at. So we've got Fraunhofer here on Earth, and he has set up some sort of prism, and he's going to have a look at the spectrum of light from the sun. Now the sun is a very, very hot, it's a very, very hot source. And this will take some copying down and explaining, and you need to make sure you've got all this. So we've got a hot source, but space actually is very, very cold. If you're out in the middle of space, sort of here, then the temperature is close to absolute zero. It's minus 272 or something Kelvin. So as you get further and further away from the sun, the gases that make up the sun aren't hot anymore. They start to cool down. So you can imagine, because over here is minus 270 Kelvin, and here is like millions of Kelvin. But the sun, it doesn't have like a hard boundary. It actually has an atmosphere of gas that surrounds it. And the further you get away from the sun, the cooler the gas gets. Very close to the sun, the gas is really, really hot. But if we can imagine that the sun's atmosphere, just like our atmosphere, extends some distance and cools down, we could imagine that surrounding the sun, like layers of an onion, are layers of gas that get progressively cooler. So I'm going to imagine that out here somewhere is part of the sun's atmosphere, which is actually a cold gas. So Fraunhofer here on Earth is looking with his prism at the light from the sun, and it's traveling out, and it is passing through successive layers of gas that get cooler and cooler, and at some distance we've got some cold gas. Okay, so what's going to happen? Near the hot source, the gases that make up the hot source, if we have a look at our energy diagrams, the sun is so hot that the heat that's produced makes the electrons jump from here to here. Okay, that's inside the sun. The electrons are very high up in the orbit of the atoms, and the electrons drop back down. Did this a little bit earlier. As the electron drops back down, we're going to get a light photon. So we've got light photons leaving the sun and traveling out. And this obviously is going to give us an emission spectrum, because energy is being emitted. Light photons are being emitted as the electron drops down. Now, out here in the cold gas area, the electrons naturally would live down the bottom. Why do they live down the bottom? Because they haven't got any energy anymore, because the gas is cold. So the electrons have gone down here, and they're at a low level, and along comes this photon of light here, and that photon of light comes along, and you can see that we've got an energy level here, and this energy gap from these two energy levels, this top one here to the bottom one here, is producing light of a certain frequency. So the electron drops down. Let's have it going from E0, E2, sorry, to E0. Got E1 there, I'm just ignoring E1. But it drops down from E2 to E0. So the energy carried by that photon is the difference in the two energy levels that we've done the calculations for. And that energy is carried away, E equals hf, that energy is carried away with this photon. So the photon here has a very, very precise energy, which is the difference between these two. Now, if the cold gas, which is situated out here in space, has exactly the same energy gap, in other words, E2 and E0 are exactly the same distance apart as the distance that caused the light to be produced in the first place, that energy of that light photon will make this electron jump up. And this is where the energy is absorbed. So what happens to this photon? It comes along here and it gives the electron in the low level, it gives it enough energy to go up. And the energy is absorbed by the electron. So that photon of light is stopped here and does not travel on to Earth. What happens then is that you would see, if there wasn't this cold gas, didn't exist at all, you would see a continuous spectrum. But because this bit of energy has been absorbed, the light has been subtracted. So you're getting lots and lots of photons of all sorts of different energies arriving here on Earth, but the photons that cause this energy to be absorbed are missing. So if that light is missing, you'll see the continuous spectrum of light from the sun with gaps, with black bands. Okay, and this leads to something called Fraunhofer lines, discovered by Mr. Fraunhofer. Now here's I'll hold this up here. Here is a continuous spectrum with a whole load of lines that are missing, and each one of these lines is called a Fraunhofer line, where energy has been absorbed. And as I mentioned earlier in this lesson, every different element has its own set of lines. So what we can do is we can look at the lines in this spectrum here, these Fraunhofer lines, and we can say, oh, I've got some lines over here at the red end, and this set of lines in the whole spectrum are produced by hydrogen. So we can say that some of this gas out here is hydrogen gas. Perhaps some of it's helium. Now, helium would have a different energy line system, and so light that's set off from the sun would cause an electron to jump a different gap in, say, helium, and so a different set of lines black lines are produced, and again they would contribute to this overall spectrum of light. Okay, so what are the Fraunhofer lines? The Fraunhofer lines are a series of missing lines that correspond to emission spectra produced by different elements, but the light is absorbed by this colder gas here. So you can get that story in one of the videos. Now, our sun has a particular chemical composition, and so you'll get a particular set of lines, and then we can deduce that the outer layers of the sun are made of hydrogen, they're made of helium, they're made of different elements. But light from different stars that we could collect and do the same experiment, not with our sun, but we could collect light from stars that we see at night. And we do this with telescopes connected with not a prism actually, but with a thing called a spectrometer. So we do exactly the same thing. We've got some sort of alien sunlight here, and that passes through layers of gas in its outer atmosphere and would arrive here viewed with a telescope on Earth, and we could then tell what gases are in the atmosphere of some sort of alien sun. Furthermore, as you'll see in one of the videos, if that cold gas is actually produced not by the sun itself, but the light passes through the atmosphere of an alien planet. Okay, I'll just move the planet down a little bit here, and I've got the atmosphere, the cold gas on an alien planet, that photon of light is going to pass through here. And if this alien planet's gas contains oxygen, then all the lines for oxygen would be submitted, and we subtracted, sorry, not submitted, would be subtracted out of the continuous spectrum, where we could tell whether an alien planet actually had oxygen in the atmosphere, which might be useful if you want to go to a planet. You do some research before you went, and we'd say, well, there's not much point in going to that planet because there's no oxygen on it. And you can actually tell by looking at the spectra the different gases that are in the atmospheres of different planets. But that's a little bit extra. That all you need to know for Fraunhofer is that we can tell what our sun is made up of, because Fraunhofer looked at the lines in our sun. His telescopes that he had when he did his work a couple of 100 years ago were not powerful enough to pick up light from individual stars, and certainly not powerful enough to pick up light from alien suns traveling through the gases of alien planets, exoplanets, if you like. He couldn't do that. And we've only been able to do this in the last few years, is actually analyze what's in gases of exoplanets. Okay, so that's just about it. I'm just going to check my notes once more, and I'm going to have a look and just have a quick look. I think that's all the things that are covered. So the learning points here is energy emitted, or is it absorbed? Here energy is emitted, here energy is absorbed. And you could describe, hopefully, if you've made some notes about what I've done, what I've been speaking about, you would be able to describe and analyze some absorption spectra of gases in the outer atmosphere of the sun, Fraunhofer lines. Okay.